let's get started. So thanks to all for coming in person, join online again. And it's my great pleasure to introduce our second guest speaker for today's lecture in climate data science, Ignacio Lopez Gomez. He's a research scientist at Google Research. His research focuses on the development of data-driven weather forecasting systems with an emphasis on extreme events and on climate modeling and analysis. He holds a PhD in environmental science and engineering from the California Institute of Technology, where he developed models of atmospheric turbulence, convection, and clouds for climate models, as well as methods for parameter estimation from indirect data. Today, he's going to talk about their recent work on generative weather forecast. Please join me in welcome Ignacio.
Thank you, Juan, and thank you everyone for having me here. It's been great so far to visit LEAP and hear about what some of you are working on. As Juan said, today I'm going to talk about some of our latest work on weather forecasting, and in particular, I'm going to talk about how generative AI technologies can be used for the emulation of weather forecast ensembles, and I'll be using diffusion models for this in this talk. And this is work that has been done together with Lisa Lee, Rob Carver, Feisha, and John Anderson at Google Research. And if there's any questions during the talk, just feel free to interrupt and ask them. Okay, so the topic of this talk is ensemble weather forecasting. What's ensemble weather forecasting? This has been the dominant approach to obtaining probabilistic forecasts of weather over the last 30 years. And what this method consists of is we are going to start from an initial state that we know from observations with some level of uncertainty. And we're going to perturb that initial state in terms of the initial condition uncertainty and also in terms of the structural uncertainty of our forecast model. And we're going to use those small-scale perturbations in the uncertainty to evolve the state of plausible states of weather given our initial conditions. And so what we end up with in this process for a given lead time, and so here I'm showing just an example for a lead time of a week, is different plausible weather states of what the weather could look like a week in advance. And that gives us, if the ensemble is big enough, that gives us an idea of what the probability of these events are. So we get a sense of the forecast uncertainty and what are the most plausible futures. And so once we have this information, these ensemble forecasts, then we can use these products to for many downstream tasks. So for instance, we can ask what's the probability of temperature exceeding a given threshold over Europe a week in advance. And this is something that I'm showing here in the schematic on the right-hand side of the slide. The problem is that performing ensemble forecasts is expensive. And so what I'm showing here is that if we have a fixed amount of compute, which here I'm drawing by this blue line, and if we were able to perform a single forecast with resolution of on the order of 10 kilometers in the horizontal for that compute, we would only be able to afford to run ensembles that run at significantly coarser resolution. So let's say 30 kilometers or so. And so there's usually this dilemma in weather forecasting when we get more compute available to us as to whether we should use that compute to increase the ensemble size or increase the resolution. So increasing the resolution, I'm sure everyone knows why that helps, because you are resolving more and more processes. So you have these subgrid scale processes that affect not only the evolution of weather, but also climate in longer timescales. And many of you here are working on improving those parameterizations. But what does increasing the ensemble size do for us? What does that bring to the table if we already have an ensemble? So I'm just going to give an example of when we would need large ensembles and why they're useful. And essentially, we're going to need large ensembles whenever we're looking at high impact rare weather events, which is something that is very important for early warning systems. And so an example that I'm giving here that is kind of related also to what we heard from Chad in the previous talk is imagine a situation where there might be a flash flooding event in New York City. And let's say that me as a user, I'm going to, if there was that flash flooding event, I would incur some losses, some economic losses, which may be that everything that I have in my basement is going to have to get thrown out, and I'm going to have to repurchase all that stuff. And then I can also associate a given cost to taking a preventive action. So in this case, it would be maybe buying sandbags and placing those sandbags somewhere so that I prevent those economic losses that I talked about before. Usually in cases where we have high impact events, the ratio between the cost of taking preventive action and the economic losses, if we weren't going to take preventive action, is very low. And so statistically, it makes sense to always follow preventive action if actually the fraud probability is going to be higher than this ratio, because otherwise it would just be more economically viable to take the losses every time this happens. But the interesting thing is what happens when the probability is kind of on the same order of magnitude as this ratio. So when it's actually like, it's not clear whether we should always take preventive action or never take preventive action, but we actually need a forecasting system for this. And it turns out that if these events are rare, that is, if the probability is of the order of C of the cost over the loss, which, as I said before, is small, then we actually need systems that have a probabilistic resolution comparable to this ratio for their forecast to be useful. Otherwise, we cannot really extract meaningful statistics from them. So if we have an ensemble, let's say of 5 or 10 members, and there's a probability of our event happening of 0.1%, we're not going to be able to extract that likelihood accurately from our ensemble. And so this example that I gave here on the left-hand side is more quantitatively articulated in the figure on the right, which comes from an article from Tim Palmer in 2002, where he's essentially looking at the relative added economic value of two forecast systems. And the one has, it's basically the same system. So the state of the IFS, I guess in 2002. And he's comparing the added value of a system with 50 ensemble members to the added value of a system with 100 ensemble members. And so what we can see is that once we increase the number of ensemble members, the users that are going to get the most value out of it are the users that have a very low cost to loss ratio. So this regime is the one where that we would characterize as high impact rare events for the reasons before. So that's one reason why we need large ensembles in weather forecasts. Since many people here are also interested in working in climate projections, I also wanted to emphasize that this is also important in climate models, and even more so. So apart from the fact that large ensembles are going to allow us to sample extremes better, in terms of the analysis of climate change, we may ask questions about whether a certain event was more likely due to climate change, or whether something that we're observing is actually cause of a forced anthropogenic response. And in order to do all this analysis, we basically have to marginalize over the internal variability of the climate projection. And for this, we also need large ensembles. And so here I'm showing another example from a paper, Milinsky et al. 2020, where they looked at what was the required ensemble size to reduce the error in the force signal for surface temperature over basically every location on Earth, and for precipitation over the historical period. And they find that if we want to reduce that error to about 1/10 of a degree in surface temperature, or 1/10 of millimeters per day in precipitation, then there's many regions in the world where we actually need more than 100 members. So this is another reason why we might need large ensembles. So what do we do about their expense? How can we reduce that? So our proposal here is that we can leverage generative AI to drastically reduce the cost of generating these ensembles through essentially emulation techniques. And in particular, the method I'm going to be talking about today is a generative emulator that enables us to sample very large weather ensembles at the cost of roughly on the order of one physics-based forecast, so basically a handful of physics-based forecasts. And if you think about a constant cost operating curve, so again, if we look at the resolution ensemble size trade-off, if we look at a physics-based ensemble, we basically have this trade-off where if we increase the ensemble size, we also need to coarsen the resolution quite severely. And our idea is to use some information from a handful of these physics-based forecasts, let's say in this case 2, and then we just get an increase in the computational cost that is marginal because we're essentially emulating these processes with generative AI techniques that are much faster than running physics-based ensembles. So our goal is to basically lower this line into this one so that we can increase the ensemble arbitrarily without compromising on the resolution. So the approach that we've taken in order to accomplish this is a method that we've called seeds. And it essentially, it's basically described in this schematic on the slide. We're trying to do generative ensemble emulation where we're going to take as input first the climatological information for some fields. So you can think about this cloud as giving us all the potential states of that particular field without initial condition information. And we're also going to consider 2 samples, in this case, from a forecasting system. So we would need basically a 2-member ensemble from a forecasting system and the climatology. And the idea is to use a diffusion model, a conditional diffusion model, to sample more plausible weather states. So we want to infill the probability forecast distribution from just a handful of states. So we're going to use these states to steer the probability distribution into one that would be given by a much larger ensemble. And for instance, we could expand to ensembles that have on the order of 500 ensemble members, which is on the order of 10 times more of the operational forecasting systems today. And so one important difference between this method and other AI-based methods that you might have read about for weather forecasting is that we're actually not doing any forecasting in time in these tasks. So I'm always taking data that comes from a fixed lead time. So let's say I'm taking the forecast of some forecasting system at a lead time DL. This could be 7 days. And I'm essentially giving you other potential samples if you were to run a bigger ensemble of that system at that same forecast time. So there's concepts such as rollout instability and changes of the spectrum and so on with time are not applicable in this case because time is not a variable. So that's a big difference with respect to models such as neural GCM or GraphCast that people might be familiar with. So how do we train a model to do this? So the approach that we've taken is, again, we're going to train a conditional diffusion model that is conditioned on K ensemble members and climatology. And we're going to feed that conditioning with some Gaussian noise to some diffusion model. And we're going to try to learn the score function within the reverse diffusion stochastic differential equation so that it gives us actually a plausible weather state. And so the labels that we're going to use for this learning method are going to be other ensemble members of the same forecast system. So essentially, if you give me an ensemble system with, say, 5 members, I'm going to use 2 condition, let's say K, or 2 condition, and then I'm going to try to predict labels that are close to any of the other 3. So this is the approach that is taken for learning in this method. And then the score function, this is the part that is learnable in our method. And in our case, we're going to use a vision transformer to parameterize the score function here and learn basically this transformation from noise to samples from the distribution that we're interested in. So for now, we've used this approach on the GEFS version 12 system. Yes, Shana?
You mentioned it, but I didn't get where did you bring in the climatology?
Oh, yes. So the climatology, so this is kind of an update state for the system where you go, so you can think of this probability as the noise, and this is going to be the final sample. And so this reverse diffusion stochastic differential equation is it's going to be conditioned on this Y. And that's where the climatology comes in. So every step we're always conditioning on the climatology and also these ensemble members. And what we are transforming is noise. Yeah. And this is different from, for instance, unconditional diffusion, where you just learn to transform a distribution to another without any more inputs. Yeah. So as I was saying, we've applied this approach to the NOAA's GEFS version 12 model, which is the operational model currently used by NOAA. Our training approach has been to train one model per lead time. As I said, we're not forecasting in time, so we can either do this or pull in time. In this case, we decided to train one model per lead time. We're going to use for conditioning two seeding forecasts for most of the results that I'm going to show today. I also have a slide where we're showing what's the sensitivity to this parameter. And for the training data, we're going to use the 20 years of daily forecast that the GEFS version 12 model has for the historical period. So this is the reforecast data set that most operational systems have available because they need this to calibrate their operational system. So this is something that we would always have in an operational system to train on. In this case, the reforecast ensemble from GEFS has 5 members. And so since we're conditioning on 2 members, for every forecast date, we can essentially choose any combination of 2 members to forecast another one. So in the end, we have 10 combinations per forecast date that we can use for training. So this is kind of a data augmentation step that we can take to train our model. And in the end, it's important to know this is a generative problem. And if you think about it, we actually have 3 labels per conditioning, because every time that we condition on 2 seeding forecasts, we might have 3 of the other possible states. So that's going to allow the diffusion model to learn about the variability in the forecast. For evaluation, we are considering the entire year of 2022. The ground truth that we're comparing our results to is year 5. And the baseline is the full GEFS version 12 operational model, which has 31 members. And the seeding forecasts are going to be taken from the operational GEFS version 12. So you could essentially download the operational GEFS forecast for today and do inference on that. That would be essentially what we did. So we trained our model using this approach, and some things that we can look at first is whether the samples actually look realistic. And so here I'm comparing samples from both our emulator on top and the full GEFS system in the bottom. And so I'm showing here a global picture of the total column vertically integrated water vapor for the 2 systems. This is one sample. And I'm also zooming into Europe for a particular day in July of 2022, where there was heat wave conditions over the Iberian Peninsula. And so you can see this important geopotential anomaly here off the west coast of Portugal. And we can see that the diffusion model is also able to capture the spatial correlations, the spatial structure of the samples, and also the intervariable correlation. So in this case, I'm plotting in color. You can see the geopotential height at 500 hectopascals, and the shadings are for the sea level pressure anomaly. And so they have similar correlations there. We can also look at how well the model is preserving the spectra. And so this is what I'm showing on the right-hand side of the slide for the temperature 2 meters above the surface. And we essentially see that the differences between our emulator and the full GEFS system are actually smaller than the difference with respect to the year 5 reanalysis that essentially comes from another operational system, IFS from ECMWF. So we can also look at different metrics at how well our model is doing. And so here I'm looking at the root mean squared error of the ensemble mean of all three ensembles, where I'm showing in blue, I'm just showing the conditioning forecast. So this is just the average of, the root mean squared error of the average of the forecast that I used to condition my model. So this is all the information that I'm giving during inference time to my model. In orange, we have the metric for the full 31-member GEFS ensemble. And in green, we have the metrics for our ensembles. In this case, since it's very cheap to generate members, in our case, we generated 512 member ensemble for this. And so what we can see is that the emulator condition on 2 ensemble members has comparable skill to the full physics-based ensemble. Of course, it's a little bit worse because we wouldn't expect it to do better in this case because we're just doing pure emulation. So the best thing we could do is actually to match it in a way because we're just in the pure emulation process. We haven't tried to correct for any issues that the model might have. But essentially, we see that they're very close together, and the gain with respect to the conditioning is very substantial. But the really useful thing about these very cheap to sample generators is that you can actually generate gigantic ensembles very fast and very cheaply. And so why this matters is shown in this example on the slide, where I'm considering the same conditions that I was showing before. So I'm showing conditions during the July 2022 heat wave over Portugal, and in particular, this is for the 7-day forecast. And in the scatter plot, just to show, I wanted to show also the intervariable correlations. I'm showing the temperature at 2 meters in degrees Celsius in the x-axis, and also the total column vertically integrated water vapor in the y-axis. The analysis, the reanalysis of what actually happened, given by ERA 5, is this star here, the brown star. The conditioning forecasts that I'm giving the emulator are shown as the blue squares, and the entire GEFS ensemble is shown as the 2 blue squares plus the orange triangles. And so one thing that we can first see from this is that none of the ensemble members from the GEFS forecast had analogs that had the same temperature, attained the same temperature or higher than the temperature that was actually observed. So in this case, we might get an estimate of the likelihood of such events. You can still get it with techniques such as kernel density estimation, but the key here is that the error bounds that you're going to get on that likelihood are very significant and are the order of magnitude of the likelihood. So it's not going to be extremely useful, and you also don't have analogs for what's happening there. In contrast, we can generate many more samples with our emulator, and in this case, we generated 16,000 samples for this, and I'm showing the probability contours here as dashed lines. And one useful thing is that we can see that we actually get analogs that are more extreme than what was observed, and we have a lot of points that are close to the star, which means that this likelihood, we're going to be able to evaluate the likelihood according to our model, at least with high precision. So that's going to allow us to make more informed decisions with quantified uncertainty. We can also look at this on a more global scale over the whole dataset by looking at metrics such as the Breyer score, which just measures what's your classification skill for certain events. In this case, we binarize the events by being class 3 sigma events in temperature. So these are events that are very warm compared to climatological conditions. And what we see is that thanks to our better sampling with our model, we are able to get a lower Breyer score than the full GEFS ensemble. And I should say that Breyer score, it's better to get a lower Breyer score. So the Breyer score is kind of an error on probability space. So you want it to be as low as possible. As I said before, we have chosen to use two-seeding forecasts for our system, for our emulator. We did compare the results for different seeding forecasts, and what we observe is that there's sort of diminishing returns in skill improvements above k = 2. So if we start using more forecast to condition, we get some improvements, but they're really marginal. I should say that for our evaluation protocol, we strictly only computed the metrics on the emulator samples. So we never considered the k samples that we would actually have. So you would imagine these metrics to actually be a little bit better, but that would give you a false sense of improvement with k because it's just taking into account the effect of those. And so This is one of the reasons why we settled for k equal to 2, because as you increase in the x-axis here, you are increasing the compute by that much. So going from 2 to 3 is 50% more expensive and so on. And yeah, so for k equal to 2, we basically get good results. So still lower CRPS than, higher CRPS, so worse than the model we're trying to emulate, but we already get better sampling of extremes. And so the question that we had is, well, can we use this approach to actually improve upon the forecast system that we're trying to emulate? And so in order to do this, we actually went back to the problem formulation and we tweaked it a little bit. So again, I'm going to here use the same diffusion model. So same conditioning. I'm going to use the same modeling approach, same architecture. What's going to change here is that the labels that I'm going to give the model when it's training are going to be a mixture between other samples from the ensemble system that I'm trying to emulate and also reanalysis data. So what I'm really doing here is, if you consider 3 probability distributions of temperature, in this case, this was the probability distribution of temperature over Mountain View for some day in 2022. What we were trying to learn before is this green curve here, which is given by the full GEFS ensemble. But we do have some information about what actually happened year 5. And we might know that maybe the ensemble that we're trying to emulate has some biases in some variables. So it might be actually good to correct for those. And so what we're proposing here is not to try to learn with a diffusion model this green curve, but actually try to learn this blue curve that corrects the biases within the ensemble. And so we've carried out this approach, and what we see is that this generative post-processing approach, which is how we call it, improves the predictive skill across the board for all the metrics and all the fields. So in this case, we should compare here this pink line, which is the generative post-processing results, to the green line, which is the one that I was showing before, the emulator. And so the improvements in some variables are bigger than others. So for instance, we know that there are small biases in 2-meter temperature in the GEFS system. And so what the generative post-processing model is able to pick up is these biases and correct for them. So we actually see not only that the root mean squared error and the CRPS are significantly improved with respect to the emulator, we're actually now outperforming the original ensemble in this variable. In other variables, it's not as clear. So if the emulated ensemble was already really good at predicting one variable, we might not see these improvements, but for the others, it actually corrects. So this is something that we found useful. We can also analyze how this generative post-processing model works for extremes. And so what we see here is that it actually also improves the performance of our model. So here again, I'm showing the Breyer score for events that are 3 sigma above the climatology, so very rare events, in very extreme events in terms of their positive anomalies, and also events that deviated -3 sigma from the event, so on the other side. And what we see is that for 2-meter temperature, we significantly outperform all other models with the generative post-processing approach. And the same is true for other variables, even though those gains are maybe a little bit less significant. Finally, one thing that we should do is we are in a way post-processing in these tasks. So we're using ERA 5 labels for training our model. So one thing that we wanted to see is whether our approach would be not only the system that it's emulating, but also a post-processed version of the model that we're emulating. And so what we did here is we took the output from the GEFS ensemble, and we performed post-processing through quantile mapping to ERA 5, so that essentially the calibrated GEFS ensemble is perfectly reliable. And then we recomputed the Breyer score for that system and compared it to our system. And so what we observe is that even though we were not targeting explicitly to have the distributions completely right with respect to the reanalysis, we're still able to beat the post-processed GEFS. So in this case, This blue line is just the score that you would get from the conditioning sample. So this is all the information that we're passing during inference to our model. In orange, we see the Breyer score for the GEFS system, just the raw forecast without recalibration. In gray, you can see the quantile mapped version of the GEFS forecast where we've recalibrated so that it's perfectly reliable. And then in pink, you can see the results for our model. So for many variables, they are basically almost the same as the post-process GEFS ensemble. And for some others, we actually get a marginal advantage. But the important thing to consider here is that in order to get these results, you need to run a 31-member ensemble and then post-processing. For this, we just need 2 members, and then we're doing everything with this very cheap emulator. So we even if we didn't beat this method, we still get a very significant reduction in the computational power. And something to note as well when comparing these two is that if we perform quantile mapping or any other form of post-processing, this is typically done by downstream users on a use case basis because they can have some not particularly useful implications for some other metrics. So for instance, if we perform quantile mapping, which is what we did here, we're going to get very good matching in statistics if we just look at pixel by pixel point-wise. But if you actually do this and look at spatial correlations, they're just going to be much worse than the original system because you are correcting every pixel independently. And so that is something that we don't get in the generative post-processing. We still conserve the intervariable and the spatial correlations well. So that's something that you get. This is sort of a general version of post-processing. And then you could, of course, do more post-processing on that if you want on that output. So then one last question that left unanswered for this particular task for generative post-processing is how do we actually blend the information from the forecasts and the reanalysis, right? So I said before that we're going to try to target a mixture of the 2 distributions, but I haven't said what kind of mixture and how we choose. And for now, the answer has been mostly empirical, which is we just tried a bunch of combinations. And so what we did is here, we essentially train models going from the pure emulation. So this would be the first methodology that I was explaining on the right-hand side. And then we increase the probability with which one of the samples of the ensemble system would be replaced by a sample from the era 5 reanalysis all the way to 100. So in this axis on 0, you would basically just train your model with labels from era 5. And what we see interestingly is that the optimum is not to train the model always with era 5. It's actually to train with a blend of them. And it seems like there's a small valley where you can choose many fractions there, but essentially if you train your model with a mixture distribution that has more weight in toward the reanalysis than towards the forecast system for this combination, so for GEFS and era 5, we're not saying that this generalizes to other models, then you typically get the best results. So from 50% to say 75% probability you would sample era 5. That's when we observe that the root mean squared error of our system is minimum, and also the things like sampling extreme events, which would be the Breyer score. Yes, Carl?
You would get information spatially, are there certain spatial locations where it might be better to use forecast versus reanalysis, or?
That's a good question. So you could do the same. You could do the same thing, but just looking at different locations and perhaps the bias. Yes, I think so. Yes, that's a very good point. So this certainly the change with respect to this parameter alpha tells you a lot about the bias. So you can see that, for instance, for the mean sea level pressure, there's a change, but it's moderate if you compare it to the difference with respect to the GFS system. But for temperature, which is the variable that we actually knew that is kind of biased in GFS with respect to era 5, you see actually this huge jump when you start using that information. So this is definitely going to be variable dependent. So maybe this would depend on the variable that you want to optimize with. One good thing that we've seen is that even though this change, the change in the magnitude is so dramatic between them, the optimum kind of seems to be on the same on the same range of alphas. So it just seems there's a region where the model can essentially use the fields to complement the information and match it better. But again, this is we've only done this analysis on the global scale. So maybe if you do it, if you were to do this regionally, if you were interested in like optimizing the model for regions, let's say California or something like that, I'm not sure that this would give you the same result. It might be something to a parameter to optimize. Definitely. Yeah, and with that, I will just end with some parting thoughts about our results. So we've seen that we can use generative AI to efficiently augment the ensemble size of numerical weather prediction systems. So in our case, we were using 2 conditioning members, and we were matching the statistics, in some cases, improving the sampling of the original system that has 31 members. So there you get a computational gain of about higher than 90% with respect to the original system, which is very significant. And so one idea there is that this saved computational expense could be devoted to increasing the spatial resolution of systems. And so if suddenly more compute is available to systems, then this ensemble size to resolution trade-off wouldn't be such a problem if we were to use these approaches to augment operational systems. Or we could also use this to, instead of increasing the number of ensemble size, increasing the size of the ensemble, we could also increase the forecast frequency. So this is it's not so important in the medium range where forecasts are actually performed very frequently. But for instance, in the subseasonal range, if you look at different operational agencies, there's agencies that are going to issue forecasts maybe 2 days a week, for instance. And actually CMWF just updated their subseasonal to seasonal forecast system, and they show that if you increase the frequency, you can, for instance, get much better prediction for the Madden-Julian oscillation that we were learning about in the previous talk. And apart from that, we've also seen that reanalysis data can be blended into the training levels to define as the generative emulator. And so far, we've done this with gridded data. Supposedly for some variables, if we had better data sets that weren't gridded, that could also be done, but that requires dealing with data that is not gridded, such as precipitation products and so on. And then just another parting thought is that there's no reason why, if this has worked for example, weather prediction, why something similar shouldn't work for certain problems in climate science, in climate projection, where we also need a lot of large ensembles in order to know what's internal variability, what's the anthropogenic forcing, and what's the probability of certain extreme events as the climate changes. And I've also added here a QR link to our article. And with that, I'll take any questions.
We do have a question online. Jatan, do you want to unmute yourself, or do you just want me to read your question out loud?
I can unmute myself. Can you hear me?
Yes, I think so.
Okay, cool. Thanks for a great talk. I was just wondering if you've compared the structure of internal variability in the physical ensembles versus what your diffusion model emulates. And is there any spatial variability to the structure of internal variability? So essentially the ensemble spread.
Oh, if we compare the spread, yes. I didn't add the. If the question was whether we compare the spread of the ensemble of our ensemble to the full GEFS ensemble, we did. I haven't added that figure in the slides, but we do have it. It's the last figure in the paper. So what we did essentially is we computed the correlation between the ensemble spread of our system and the full GEFS system, and what we see is that correlation is higher than the correlation with respect to the conditioning members. So we are actually learning some dynamical features there. We're learning to infill the attractor, if you will, close to the members. And what we also verified is that if we actually when we were dealing with lead times that are beyond the medium range, so let's say like 16 days, that our model had higher correlation as well than climatology, because at some point all these distributions, all the uncertainty is going to converge to climatology. And so what we see is that our model is able to learn that transition, but still has a bigger correlation with the full ensemble.
Thank you.
Great talk. I have a quick question. It looked like you use like temperature data and like wind data a lot for the forecasting, and like temperature is kind of normally distributed. How would could this be applied to like weather patterns that are like not so normally distributed? Like, precipitation is not going to be a bell curve, so it's kind of hard to like,
right.
I don't know, like the extremes are hard to find, I guess.
Yeah. So that's a very good question. So one thing that, since this was like our first approach to the problem, we wanted to focus on fields where both we have good reanalysis data and also that the data is not too complicated to model. So that's one reason why we explicitly left precipitation out of this. Of course, we understand that precipitation is very important. So this is something that we're looking at the moment, but we just know that basically, I think anyone that has worked with like data-driven methods and then tries something on temperature and then on precipitation, there's a jump there. And so we didn't want to do that jump for now, but that's something that we have in our mind. Thank you. Yeah.
We have another question online. Parsa, would you like to unmute yourself? Parsa, would you like to unmute yourself or type?
Hi. Thank you for the time, and thanks for the interesting talk. I was talking and I was muted. So yeah, this was quite interesting. My question is, I'm curious about, if I remember correctly, you mentioned something of the order of 1,000 ensembles or thousands of ensembles that you generated in order to sample that extreme event that you showed. So my question is, do we have any sort of objective measure of how many ensembles we're going to require to be able to sample this space? So basically what I mean is that, do we have any measure of the equivalent number of for the number of ensembles that we need for this model to sample an equivalent distribution of the numerical model?
Yeah, yeah, that's a good question. So the answer is that yes, we can get it. So the way that and I didn't add this here, but we did that, which is that you can essentially for any of these forecast systems, any of these forecast ensembles are going to assign a probability to this event if you just ask what that probability is. And so what we did is we fit a Gaussian kernel. So we basically performed kernel density estimation supported on the GEFS full data for this particular date. And the probability of it happening was about 0.7% according to the kernel density. And so what that tells us is that, if we have a probability of it happening of 0.7% and we only have like 30 members, then the uncertainty on that 0.7%, like the error bars are going to be very, very large. They're actually going to be larger than that 0.7%. So that tells you that you would need, so from that, it depends on the p-value that you want to assign. So depending on the p-value, you're going to get a number of ensemble members that would be required to get that. So that's kind of similar to how the authors got this map here, which is you tell me the acceptable error, I'm going to tell you how many ensemble members you get. And so for a p-value of 0.05 for this particular measurement, if I remember correctly, I think you would have needed about 130 ensemble members. And the order of magnitude for the ensemble emulator was similar. So you can, again, do the same thing you can also perform kernel density estimation with the emulated ensemble. The probability was also around 1%, but the uncertainty bounds were very, very small here because we had 16,000 samples. So what this allows you to do is just essentially reduce the error bars of the likelihood as much as you want. But of course, this is just with respect to the sampling error, not with respect to other errors. But yeah, good question.
Thank you.